Somewhere in the constellation Sextans, for 1,500 light years from Earth, a cosmic horror story is unfolding right now. A dead star is devouring its living companion, draining it of its very essence. And in the process, it's doing something that has never been observed before in the history of astronomy. Every few seconds to minutes, this stellar vampire launches massive blobs of superheated plasma into the void of space at nearly the speed of light. Scientists call these ejections cosmic cannonballs, and each one contains enough matter to reshape our understanding of how dead stars behave. The object responsible for this violence is called Pulsar J1023 plus 0038, or J1023 for short. It's a pulsar, the spinning corpse of a star that died in a catastrophic explosion millions of years ago. But J1023 is no ordinary pulsar. It belongs to an extremely rare class of objects known as transitional millisecond pulsars, and it's currently the most studied member of this exclusive cosmic club. What makes it special is that astronomers caught it in the act of transformation, switching between two completely different states of existence in real time. This has never happened before with any other known object in the universe. To truly understand why J1023 matters, we need to go back to the beginning. Not just the beginning of this particular system, but the beginning of how stars like this are born. And that story starts with death. When a massive star exhausts its nuclear fuel, it can no longer support itself against the crushing weight of its own gravity. The core collapses in a fraction of a second, and the outer layers are blown away in a supernova explosion that can outshine an entire galaxy. What remains is something extraordinary, a neutron star, one of the most extreme objects in the known universe. A neutron star is essentially a giant atomic nucleus about 20 kilometers across, roughly the size of a city like Paris or Manhattan. Yet packed into this tiny volume is more mass than our entire sun, about 1.4 solar masses on average. The density is so extreme that a single teaspoon of neutron star material would weigh about 6 billion tons. If you could somehow scoop up all 8 billion humans on Earth and compress them into the density of a neutron star, they would fit into a space smaller than a sugar cube. This density creates gravitational forces that are almost impossible to comprehend. If you dropped a marshmallow onto the surface of a neutron star, it would accelerate so quickly that by the time it hit the surface, it would release energy equivalent to 1,000 hydrogen bombs detonating simultaneously. The surface gravity is about 200 billion times stronger than Earth's gravity. If you weighed 70 kilograms on Earth, you would weigh about 14 trillion kilograms on a neutron star. That is for the brief fraction of a second before you were smeared across the surface as a thin layer of plasma. But density and gravity are just the beginning of neutron star extremes. These objects also possess the most powerful magnetic fields in the known universe. The strongest neutron star magnetic fields are nearly 100 trillion times stronger than Earth's magnetic field. Even the weakest neutron star magnetic fields are 100 million times Earth's, which is itself about 100 times stronger than any steady magnetic field we can generate in a laboratory. These magnetic fields are so intense that they fundamentally alter the structure of atoms. In a magnetic field of around 1 trillion Gauss, the ground state binding energy of hydrogen rises from 13.6 electron volts to 160 electron volts. The atoms themselves become distorted, stretched along the magnetic field lines like cosmic taffy. The interior of a neutron star is even more bizarre than its surface. If you could somehow drill down through the crust, which is about 1 mile thick and made of extremely dense crystalline matter, you would encounter progressively stranger forms of matter. The outer layers contain heavy atomic nuclei, like iron, 56, embedded in a sea of degenerate electrons. But as you descend deeper and the pressure increases, the equilibrium favors heavier and more neutron-rich elements, nuclei that don't exist anywhere else in the universe. At densities around 4 times 10 superscript 1 grams per cubic centimeter, something remarkable happens. Some neutrons become unbound from their nuclei and begin to flow freely between them. This region is called the inner crust, and it's where the famous nuclear pasta exists. As the density increases further, the nuclear matter begins to take on strange shapes: spheres, cylinders, slabs, tubes, and finally, before the transition to the core, a phase that looks like Swiss cheese with spherical holes. These shapes are called gnocchi, spaghetti, lasagna, bucatini, and Swiss cheese, respectively. Nuclear physicists have a sense of humor about their pasta. The core of a neutron star is the most mysterious region of all. Here, the density exceeds the density of atomic nuclei themselves. We don't know for certain what exists at these pressures, because we cannot recreate such conditions in any laboratory on Earth. The matter might consist of free quarks, no longer confined within neutrons and protons. There might be exotic particles called hyperons, which contain strange quarks. There could be condensates of pions or kaons. The core of a neutron star is essentially a natural laboratory for physics at energy scales we cannot otherwise access. Now, here's where the story takes an interesting turn. When neutron stars are born, they rotate. And thanks to the conservation of angular momentum, the same principle that makes a figure skater spin faster when they pull their arms in, the collapse of a stellar core into something city-sized causes the rotation rate to increase dramatically. Some neutron stars spin hundreds of times per second. The fastest known pulsar completes over 700 rotations every second. Its equator is moving at about 24% of the speed of light. Combined with their powerful magnetic fields, this rotation produces beams of electromagnetic radiation that sweep through space like lighthouse beams. When these beams happen to point toward Earth during part of the rotation, we detect regular pulses of radio waves, X-rays, or gamma rays. This is what makes them pulsars, pulsating radio sources. The regularity of these pulses is so precise that some pulsars rival atomic clocks in their time-keeping accuracy. But pulsars slow down over time. Every rotation drains a little energy from the neutron star, carried away by radiation and particles streaming into space. Over millions of years, a pulsar that once spun hundreds of times per second gradually winds down, its pulses becoming weaker and more spaced out until eventually it becomes too faint to detect. The cosmic lighthouse goes dark. This should have been the fate of J1023. It should have been just another old, slow, dying pulsar. But something changed its destiny. it had a companion. J1023 is not alone in space. It orbits another star, locked in a gravitational dance that brings them incredibly close together. The companion is a small star with about 1/5 the mass of our Sun, and it orbits the pulsar every 4.75 hours. For perspective, our Moon takes about 28 days to orbit Earth. This binary system is so compact that the entire orbit could fit inside the Sun. And this is where the vampire story begins. When two stars orbit each other this closely, the more massive one, in this case, the pulsar, exerts powerful tidal forces on its companion. There's a mathematical surface called the Roche lobe that marks the gravitational boundary around each star. If a star expands or is pulled beyond its Roche lobe, its matter begins to fall toward the other star. In the J1023 system, the companion star has overflowed this boundary, and its material is being stripped away by the pulsar's gravitational grip. But the matter doesn't fall directly onto the pulsar. Because of the orbital motion, the stolen material carries angular momentum, which causes it to spiral around the pulsar rather than plunging straight in. This creates a disk of superheated gas called an accretion disk. The disk glows brightly across the electromagnetic spectrum as the matter gradually spirals inward, heated by friction and gravitational compression to millions of degrees. This process of accretion has a remarkable side effect. It spins up the pulsar. The matter falling onto the neutron star carries angular momentum, and as it's added to the star, that angular momentum is transferred to the star's rotation. Over hundreds of millions of years, this process can take an old, slow pulsar and resurrect it, spinning it back up to millisecond rotation periods. These rejuvenated pulsars are called recycled pulsars or millisecond pulsars, and they represent a second life for stellar corpses that should have faded into obscurity. J1023 was discovered in 2007 as a millisecond pulsar, spinning 592 times per second with extraordinary regularity. Its radio pulses swept past Earth like clockwork, and for astronomers, it was an interesting but not extraordinary addition to the growing catalog of millisecond pulsars. No one suspected that within a few years, it would do something unprecedented. In 2013, everything changed. The regular radio pulses from J1023 suddenly disappeared. At the same time, the system began to glow much more brightly across visible light, ultraviolet, X-ray, and gamma-ray wavelengths. Astronomers quickly realized what had happened. The pulsar had begun actively feeding from its companion again. An accretion disk had formed around the neutron star, and it was now caught in the act of transformation, transitioning between its pulsar state and its accreting state. This was monumental. Astronomers had long theorized that millisecond pulsars were created through accretion, but they had never directly observed the system switching between these two states. J1023 became the prototype for a new class of objects, transitional millisecond pulsars. To date, only 3 such objects are known, and J1023 remains the most accessible and best studied. But the surprises were just beginning. As astronomers monitored J1023 in its accreting state, they noticed something very strange. The brightness of the system wasn't constant. It was flickering switching between two distinct levels, a high mode and a low mode, sometimes staying in one state for several minutes, sometimes for just a few seconds before abruptly switching again. No one could explain why. For nearly a decade, this behavior remained a mystery. Various theories were proposed. Perhaps the accretion disk was unstable. Perhaps the magnetic field was somehow modulating the flow of matter. Perhaps there were instabilities in the pulsar wind, the stream of particles constantly blowing away from the rapidly rotating neutron star. None of these explanations fully fit the observations. Then, in June 2021, an international team of astronomers decided to throw everything they had at the problem. They coordinated observations across 12 different telescopes and instruments, both on the ground and in space. The ground-based arsenal included the Very Large Telescope and the Atacama Large Millimeter/Submillimeter Array, both operated by the European Southern Observatory in Chile. The space-based instruments included ESA's Eximum Newton X-ray Telescope, NASA's Swift and NICER observatories, and the Hubble Space Telescope. Over 2 nights, this unprecedented multi-wavelength campaign caught J1023 switching between high and low modes more than 280 times. By watching the system simultaneously across radio waves, millimeter waves, visible light, ultraviolet, X-rays, and gamma rays, the team could see how different parts of the system behaved during each transition. And what they discovered was astonishing. The key observation came from ALMA, the radio telescope array that could detect millimeter wavelength radiation. Just before the system switched from high mode to low mode, ALMA detected a brief flare, a sudden burst of radio emission. This was the smoking gun. The flare indicated that something was being ejected from the system at precisely the moment the brightness dropped. Here's what the astronomers pieced together. During the high mode, matter from the companion star streams toward the pulsar and collects in a puffy accretion disk. At the same time, the pulsar itself is continuously blowing out a powerful wind of charged particles. This pulsar wind slams into the infalling matter, creating a massive shock where the two flows collide. The collision heats the matter to extreme temperatures and makes the system glow brightly in X-rays, ultraviolet, and visible light. But this situation is inherently unstable. The pulsar wind keeps pushing against the infalling matter, and periodically, it wins. When the wind overcomes the infall, it ejects a blob of matter from the system in the form of a narrow jet perpendicular to the accretion disk. This is the cosmic cannonball. The ejection happens in just tens of seconds, roughly the time it takes Usain Bolt to run 100 meters, and it carries enormous amounts of matter out into space. Once the blob is ejected, the pressure drops. The system switches to low mode, becoming much fainter because there's less hot matter near the pulsar to glow. But the companion star is still losing mass, so new material continues to flow toward the pulsar. The accretion disk rebuilds, matter accumulates, and eventually the pulsar wind again becomes overwhelmed by the infalling material. The system returns to high mode, and the cycle begins again. The researchers found that J1023 spends about 70% of its time in the high mode and 30% in the low mode. The switching happens on timescales as short as 10 seconds, but their instruments could only sample data at certain speeds. The lead author of the study, Maria Cristina Baglio from New York University Abu Dhabi, suggested that the actual switching might happen even faster, perhaps as quickly as a tenth of a second, roughly the time it takes to blink. This discovery solved a decade-old mystery, but it raised new questions. Is J1023 unique? Or are there other pulsars exhibiting this behavior that we simply haven't observed closely enough? What determines the exact timing of the ejections? How much total mass is the pulsar ejecting over time? And how does this affect its evolution? How does the companion star respond to having its matter continuously stripped away? The companion star in the J1023 system is already paying a heavy price for its proximity to the pulsar. Transitional millisecond pulsars like J1023 belong to a class of binary systems that astronomers have nicknamed spiders because of their predatory behavior. Within this class, there are two main subtypes: black widows and redbacks, named after spiders known for cannibalistic mating behavior. Black widow pulsars have very low mass companions, less than about 0.05 solar masses. Essentially, the pulsar has already devoured most of its partner. Redbacks, like J1023, have more massive companions, typically between 0.1 and 0.4 solar masses. These are stars that still have significant mass to give, but are being progressively consumed. Over hundreds of millions of years, redbacks can evolve into black widows as the companion is whittled down to almost nothing. The ultimate fate of these systems is even more dramatic. Given enough time, typically billions of years, the pulsar can completely ablate its companion, reducing it to a planetary mass object or evaporating it entirely. This is likely the explanation for the roughly 30% of millisecond pulsars that are found alone without any companion. They're not loners by birth, they're widowers. They destroyed their partners. Some systems reach even stranger endpoints. There's a pulsar called Pulsar J1023-1438 with a companion that has a mass similar to Jupiter, but a density at least 23 grams per cubic centimeter, about 23 times denser than water and comparable to the density of platinum. This companion is thought to be the exposed core of a white dwarf star, stripped of its outer layers by the pulsar. It's essentially a planet-sized diamond orbiting a dead star. But let's return to J1023 and consider what's happening there in more detail. The physics of the mode switching involves a fascinating interplay between several extreme phenomena: the pulsar wind, the accretion disk, the magnetic field, and relativistic jets. The pulsar wind is perhaps the most important player, because J1023 rotates 592 times per second and has an extremely strong magnetic field. It acts like a giant electromagnetic dynamo. The rapid rotation combined with the magnetic field accelerates charged particles, electrons and positrons, to nearly the speed of light and flings them outward in all directions. This is the pulsar wind, and it carries an enormous amount of energy. In an isolated pulsar, this wind would simply stream out into space, eventually slowing down and creating a structure called a pulsar wind nebula. But J1023 isn't isolated. It has matter trying to fall onto it, and the pulsar wind collides with this infalling matter at the inner edge of the accretion disk. This collision creates what physicists call a shock front, a boundary where the supersonic pulsar wind suddenly decelerates and converts its kinetic energy into heat. The temperatures at this shock can reach billions of degrees. Electrons in the shock are accelerated to extremely high energies and emit synchrotron radiation, a type of electromagnetic emission that occurs when charged particles spiral around magnetic field lines at relativistic speeds. Recent observations with the Imaging X-ray Polarimetry Explorer (IXP) satellite have detected polarized X-ray emission from J1023 during its high mode. Polarization is a property of light that tells us about the direction of the electric field oscillations, and it provides crucial information about the emission mechanism and geometry. The degree of polarization observed, about 12%, is higher than what's seen in typical accreting neutron stars, suggesting that the emission mechanism in J1023 is fundamentally different. The polarization data support a picture where the X-ray and optical emission both come from the same process. Synchrotron radiation from electrons accelerated at the shock between the pulsar wind and the accretion disk. This is a significant finding because it means the emission is not powered by accretion in the traditional sense, matter falling onto the neutron star surface, but rather by the pulsar wind heating up the surrounding matter. This has profound implications. It means that J1023 represents a unique regime of neutron star behavior, somewhere between a pure rotation-powered pulsar and a pure accretion-powered X-ray binary. It's a hybrid, drawing energy from both the pulsar's rotation and the gravitational potential of the infalling matter, but in a way that involves complex interactions between the two. The jets that produce the cosmic cannonballs are another remarkable feature. Jets are common in astrophysics. They're seen from black holes, from young stars, from active galactic nuclei, but they're relatively rare in neutron star systems. When they do appear, they typically emerge perpendicular to the accretion disk, collimated into narrow beams by magnetic fields. In J1023, the jets seem to be intimately connected to the mode switching. The ALMA observations showed that the radio flare associated with jet ejection occurs precisely at the transition from high mode to low mode. This suggests that the jet launch is what triggers the mode switch. The ejection of the hot matter blob removes the material that was causing the bright emission, and the system drops into its fainter low mode. The speed of the ejected matter is also extreme. Estimates suggest the blobs are moving at significant fractions of the speed of light. At these velocities, relativistic effects become important. Time dilation causes clocks moving with the blob to run slower than clocks at rest. Length contraction compresses the blob along its direction of motion. And relativistic beaming causes the radiation from the blob to be concentrated in the direction of motion, making the blob appear brighter when it's moving toward us and fainter when it's moving away. Understanding these cosmic cannonballs is not just an academic exercise. The process of jet formation and particle acceleration in extreme environments is one of the outstanding problems in astrophysics. How do magnetic fields collimate the outflow into such narrow beams? How are particles accelerated to such high energies? What determines the mass and velocity of each ejection? J1023, by providing a relatively nearby and well-studied example, offers a unique laboratory for addressing these questions. The distance to J1023, about 4,500 light-years, is close enough that we can observe the system in unprecedented detail, but far enough that we're seeing it as it was 4,500 years ago. When the light we detect today left J1023, the ancient Egyptians were building the Great Pyramids. The Mesopotamian civilization was flourishing in the Fertile Crescent. Stonehenge was a relatively new monument. Human writing was just a few centuries old. Over the time that light has been traveling toward us, the J1023 system has continued its relentless cycle. If the mode switching has remained consistent, the system has switched between high and low modes roughly 50 billion times since that light was emitted. 50 billion cosmic cannonballs have been launched into space, carrying away mass from the accretion disk, each one a brief, violent spasm in an ongoing cosmic drama. The implications for the long-term evolution of the system are significant. Every blob of matter ejected is mass that doesn't make it onto the pulsar. If the ejection rate is high enough, it might actually prevent the pulsar from gaining mass despite the ongoing accretion from the companion. Or the mass loss might be only a small fraction of the total accretion rate, representing a kind of cosmic spillage rather than a fundamental barrier. The companion star, meanwhile, continues to lose mass. Red dwarf stars like J1023's companion can survive this kind of ablation for billions of years because they're so much larger than the pulsar and have substantial mass reserves. But eventually, the balance will shift. The companion will shrink as its mass decreases, possibly eventually becoming completely engulfed by the pulsar's radiation or reduced to a tiny remnant. There's another factor that affects the system's evolution: gravitational radiation. According to Einstein's general theory of relativity, any two masses orbiting each other emit gravitational waves, ripples in the fabric of space-time. For ordinary binary stars, the energy loss to gravitational waves is negligible over astronomical timescales. But for extremely compact binaries like J1023, where the orbital period is just 4.75 hours, gravitational wave emission becomes significant. As the system loses energy to gravitational waves, the orbit shrinks, bringing the two stars closer together. This increases the rate at which matter is transferred from the companion to the pulsar, potentially intensifying the feeding process. Over billions of years, gravitational wave emission could drive the companion to spiral ever closer to the pulsar, until eventually they might merge. What would happen in such a merger is unclear. If the combined mass exceeds about 2 to 3 solar masses, the maximum mass a neutron star can sustain against gravitational collapse, the result would be a black hole. If the mass is below this threshold, the result might be a rapidly spinning, extremely hot neutron star that would gradually cool and settle down over millions of years. But we're getting ahead of ourselves. For now, J1023 continues its remarkable behavior, and astronomers are planning even more detailed observations to unravel its remaining mysteries. The European Southern Observatory is currently building the Extremely Large Telescope, or ELT, in the Atacama Desert of Chile. With a main mirror 39 meters in diameter, it will be the largest optical telescope ever constructed. When it comes online in the late 2020s, it will be able to observe J1023 with unprecedented resolution and sensitivity. The researchers who discovered the mode-switching mechanism are already planning what they'll do with this new capability. According to Sergio Campana, a research director at the Italian National Institute for Astrophysics and one of the study's co-authors, the ELT will allow them to understand how the amount, distribution, and dynamics of the infalling matter around the pulsar are affected by the mode-switching behavior. They'll be able to watch the accretion disk in much finer detail, tracking how matter flows and accumulates before being ejected. Other instruments will contribute as well. The next generation of X-ray telescopes, such as the proposed Athena mission from ESA, will provide spectroscopic information about the composition and velocity of the hot gas in the system. Radio telescope arrays, like the Square Kilometre Array, currently under construction in South Africa and Australia, will detect the faintest radio emission from the jets and potentially track individual blobs as they propagate away from the pulsar. There's also the tantalizing possibility of detecting gravitational waves from the J1023 system. While the current gravitational wave detectors like LIGO and Virgo are sensitive primarily to the violent gravitational waves produced by mergers, future space-based detectors like LISA, the Laser Interferometer Space Antenna, might be able to detect the continuous gravitational wave emission from compact binaries like J1023. This would provide an entirely new way to probe the system's dynamics. The study of J1023 also has broader implications for our understanding of stellar evolution. Millisecond pulsars and their progenitor systems play important roles in several areas of astrophysics. First, they're natural laboratories for testing the equation of state of matter at extreme densities. The equation of state describes how pressure relates to density, and it determines the maximum mass a neutron star can have before collapsing into a black hole. Different theoretical models of nuclear matter predict different equations of state, and measuring neutron star masses and radii can distinguish between these models. The most massive known neutron stars have masses around 2 solar masses, which has already ruled out some soft equations of state that predicted lower maximum masses. Second, millisecond pulsars are extraordinarily precise clocks, and this makes them useful for fundamental physics experiments. Arrays of millisecond pulsars are being used to detect very low-frequency gravitational waves, ripples in space-time caused by supermassive black hole binaries in distant galaxies. By monitoring the timing of pulses from multiple millisecond pulsars across the sky, astronomers can detect the tiny correlated shifts in arrival times that would be caused by passing gravitational waves. In 2023, several pulsar timing arrays announced evidence for such a gravitational wave background, opening a new window on the universe. Third, binary millisecond pulsars provide some of the most stringent tests of Einstein's general theory of relativity in the strong field regime. By measuring the orbital decay of these systems due to gravitational wave emission and comparing it to the predictions of general relativity, astronomers can verify the theory to extraordinary precision. So far, general relativity has passed every test thrown at it by pulsar observations. J1023 contributes to all these areas. Its mass can be estimated from orbital dynamics, constraining the equation of state. Its mode switching provides information about the interaction between rotation-powered and accretion-powered emission, which affects how its pulses can be used for timing experiments. and its status as a transitional system means it can be studied in multiple states, providing a more complete picture of neutron star binary evolution. There's also a human dimension to this story. The discovery of J1023's mode-switching mechanism was the result of an extraordinary international collaboration. The 2021 observing campaign involved researchers from institutions across the globe. New York University Abu Dhabi, the Italian National Institute for Astrophysics, the Institute of Space Sciences in Barcelona, and many others. The observations required coordinating telescope time across multiple facilities on different continents and in space, synchronizing observations to within seconds to ensure all instruments were looking at the same events. This kind of multi-wavelength, multi-instrument coordination is becoming increasingly common in astronomy, as researchers recognize that the most interesting cosmic phenomena often reveal different aspects of themselves in different parts of the electromagnetic spectrum. X-rays show us the hottest gas closest to the neutron star. Optical light reveals the cooler material in the outer disk and the contribution from the companion star. Radio waves trace the jets and the pulsar wind. Only by combining all these views can we get a complete picture. The lead author of the discovery paper, Maria Cristina Baglio, described the experience of witnessing the cosmic cannonball ejections in vivid terms. In her words, they had witnessed extraordinary cosmic events where enormous amounts of matter were launched into space within a very brief time span from a small, dense celestial object rotating at incredibly high speeds. For astronomers who spend much of their time looking at static images and analyzing data tables, directly watching a neutron star system do something dramatic in almost real time is a rare and exciting experience. Let's pause to consider the sheer improbability of us being able to observe J1023 at all. The universe is about 13.8 billion years old. The Milky Way galaxy contains hundreds of billions of stars, and only a tiny fraction of these have ever become neutron stars. Of those neutron stars, only a subset are in binary systems where they can be spun up into millisecond pulsars. Of those, only a tiny handful are transitional systems caught in the act of switching between states. And of those, only one, J1023, happens to be close enough and bright enough for us to study in such detail, and happens to be at the right orientation for us to observe its mode switching and jet ejections. We are extraordinarily lucky that nature has provided us with this cosmic laboratory within observing distance. If J1023 were in a distant galaxy, or if its jets were pointed away from us, or if its mode switching happened too quickly or too slowly for our instruments to detect, we might never have understood how these systems work. The universe owes us nothing, and yet here is this gift, a vampire pulsar caught in the act, teaching us about the most extreme physics in the cosmos. The physics revealed by J1023 touches on some of the deepest questions in astrophysics. How does matter behave at densities beyond anything we can recreate on Earth? What is the nature of the transition between matter composed of neutrons and more exotic forms like quark matter? How do magnetic fields of trillion Gauss strength shape the flow of plasma around neutron stars? How are particles accelerated to nearly the speed of light in astrophysical jets? How do binary star systems evolve over billions of years under the competing influences of mass transfer, angular momentum loss, and gravitational wave emission. Each observation of J1023 provides another piece of the puzzle. Each mode switch, each cosmic cannonball, each flare and flicker contains information about the underlying physical processes. And because J1023 switches states hundreds of times per day, astronomers have abundant opportunities to gather data. It's like having a cosmic physics experiment that runs continuously 24 hours a day, 7 days a week, generating new results every few seconds. The contrast with laboratory physics is striking. In particle physics, experimenters might wait months or years for a single event of interest, a rare particle decay, an unusual collision, a fleeting glimpse of new physics. In J1023, the interesting events happen constantly. The challenge is not finding phenomena to study, but keeping up with the flood of data and extracting meaningful insights from the complexity. This is where theory becomes essential. Observational data, no matter how abundant, is useless without a theoretical framework to interpret it. The model proposed by Baglio and colleagues, with a pulsar wind colliding with infalling matter, heating it up, and periodically ejecting blobs when the wind overcomes the infall, is a theoretical framework that makes sense of the observations. But it's still a simplified picture. The real system is far more complex, involving magnetohydrodynamics, radiation transport, general relativistic effects, and particle physics at extreme energies. Developing accurate models of systems like J1023 requires sophisticated numerical simulations. These simulations divide space into millions or billions of tiny cells and calculate how matter and radiation move from cell to cell according to the laws of physics. They track the magnetic field as it twists and reconnects. They follow particles as they're accelerated to high energies. They compute the emission of radiation across the entire electromagnetic spectrum. Such simulations require enormous computing power. Modern supercomputers can now begin to tackle these problems, but even the most powerful machines struggle with the full complexity of neutron star systems. The range of scales is enormous, from the 20-kilometer neutron star itself to the million-kilometer accretion disk to the light-year scale jets and nebulae. The timescales range from milliseconds, the rotation period, to minutes, the mode switching, to years, the orbital evolution, to billions of years, the system's lifetime. No single simulation can capture all of this. Instead, researchers use a hierarchical approach, simulating different aspects of the system at different resolutions and combining the results. Close to the neutron star, they use high-resolution simulations that capture the shock between the pulsar wind and the disk. At larger scales, they use simpler models that treat the inner regions as boundary conditions. The results are then compared with observations to check whether the theoretical predictions match what we actually see. For J1023, this process of model testing is ongoing. The basic picture of mode switching via blob ejection seems secure, but many details remain uncertain. What determines the exact timing of each ejection? Is there a threshold amount of matter that must accumulate before the ejection occurs? How does the pulsar's rotation phase affect the process? Why is the system in high mode 70% of the time rather than 50% or 90%? These questions are not merely academic. Understanding the physics of J1023 in detail will help us understand other extreme objects in the universe. Black holes, for example, also have accretion disks and jets, and the physics of jet formation may be similar even though the central object is fundamentally different. Active galactic nuclei, powered by supermassive black holes billions of times more massive than our Sun, launch jets that extend for millions of light years and affect the evolution of entire galaxies. The principles learned from studying J1023 may illuminate these much larger systems. There's also the possibility that J1023 like behavior is more common than we currently realize. Before the intensive observing campaign of 2021, the mode switching in J1023 was known but unexplained. Now that we understand what's happening, astronomers can look for similar signatures in other systems. Perhaps there are other transitional millisecond pulsars exhibiting mode switching that we've overlooked because we weren't looking carefully enough. Perhaps there are other classes of objects, X-ray binaries, cataclysmic variables, young stellar objects, that show analogous behavior driven by similar physics. Science often works this way. A detailed study of a single remarkable object reveals new phenomena and new principles, which then turn out to be widespread once we know what to look for. J1023 may be the Rosetta Stone of high-energy astrophysics, unlocking mysteries not just about transitional pulsars, but about accretion and ejection throughout the universe. As we continue to observe J1023 in the coming years and decades, we can expect more surprises. The universe has a habit of being more interesting than our theories predict. Perhaps J1023 will transition back to its pulsar state, allowing astronomers to study it in that configuration with modern instruments. Perhaps it will enter an outburst state with much higher accretion rates and even more dramatic behavior. Perhaps it will do something entirely unexpected, forcing us to revise our models once again. For now, J1023 continues its eternal dance of death, draining the life from its companion star, launching cosmic cannonballs into the void, switching between brightness states in a rhythm that has persisted for millions of years and will persist for millions more. It's a reminder that even dead stars can live dramatic lives, and that the universe, for all its vastness and age, is still full of wonders waiting to be discovered. The vampire pulsar feeds on. The cosmic cannonballs fly. And somewhere in the constellation Sextans, for 1,500 light years away, the most extreme physics in the universe plays out in real time. Second by second, mode switch by mode switch, as it has done since long before humans existed and will continue to do long after we're gone. We are privileged to watch, to wonder, and to understand.